Hi, everybody. This video is going to give you an overview of the structure of a neuron and a quick overview of the action potential. So let's start with the structure of a neuron. Now, neurons can be in different categories. There are multipolar neurons, unipolar neurons, bipolar neurons, but the neuron that I asked you to label in your notes was a multipolar neuron. So we usually see these as motor neurons. And it looks something like this. You know that I'm a terrible drawer, so bear with me on this. So the basic structures of a neuron are the branches, which are called dendrites. And then this circular structure here, which has the central nucleus. This circular structure is referred to as the soma, or you can also see it referred to as the cell body. So the soma, or the cell body, contains the cytoplasm, the nucleus, and all of the organelles of the neuron. And then, actually, let's make this more like a tube structure. Where the soma, or the cell body, meets the long extension is called the axon hillock. And then this long extension is called the axon. And the branches over here are called the synaptic terminals. Oops, sorry about that. Synaptic terminals. Okay, so again, let's review. The dendrites are the branches, and then we have this round circular structure called the cell body, or the soma, which contains the dark stained nucleus. The long extension is called the axon. We can always think of an axon or this long extension like a wire. And then branching off of the axon are the synaptic terminals. If you were to think about the neuron as like a wire, you would think of this region here, the dendrites, as the input zone, or the receiving part of the neuron. And then information flows this way. So the synaptic terminals would be our output area. So I hope that makes sense. One other thing I want to mention is that we have special neuroglial cells. Glial cells are the support cells of the neuron that cover the axon with a fatty sheath. And that's fatty sheath is just lipid. Lipid is, we know what fat looks like. You can think of like chicken fat. Chicken fat is white and glistening, and that's what this substance is. It's just a lipid. And this yellow substance is called myelin. I'm going to write it here. I know I wrote it. I drew it in yellow, but hopefully you can see that on your screen. Myelin. It's a fatty sheath that helps insulate the axon. And we know that neurons conduct electrical signals, right? We always say that nervous tissue helps communicate and coordinate different body systems and helps to do so via electrical signals. Well, we'll talk about those electrical signals in a moment. But just like the wires in our house, electrical wires have to be insulated. So the electricity can run through the wire and it can be insulated so the signal goes quickly. Same thing with myelin. When myelin is around and myelin is wrapped around the axon, myelin acts as an insulator. So remember, myelin is fat, but it acts as an insulator. So any neuron that has myelin associated with it will conduct electrical signals faster than any neuron that is not myelinated. And, throughout the body, we have many neurons that have myelin, but there are some neurons that do not have myelin, and that's normal. One condition or disease that we see where an individual may have had myelin, and then they have an autoimmune disease where their body would attack the myelin on the axons of their neurons. That disease is called multiple sclerosis. And that's an autoimmune disorder where the myelin degrades because the person's body is attacking the myelin. And what we see is that the electrical signals of their neurons kind of move slower or dissipate. And you see that in the signaling becoming weaker from, let's say, the brain to the muscles. So the muscles move a little bit slower. So you can think of MS and myelin together. I'm sure, unfortunately, someone knows someone who has multiple sclerosis. Okay, so that's the picture of our neuron. I'm going to clear my drawings. Now I want to talk more about the electrical activity of our neurons. And before I draw a neuron, I'm just going to draw a regular cell. And normally in class, whenever I draw a regular cell, it's a circle shape. You know that cells come in all different shapes. They're cube shaped, column shaped, neuron shaped. But I'm just going to draw it as a simple circle because that's easiest for me. Now, in a previous chapter, what feels like a long, long time ago, it's only been a couple weeks, we talked about an ion distribution. So the inside of the cell has different concentrations of ions compared to the outside of the cell. And I'll remind you that the inside of our cell has a high concentration of potassium ions. And you can see that I drew it here with a large K inside the cell compared to a small k outside the cell. So that means that the intracellular fluid has a higher concentration of potassium ions compared to the extracellular fluid. The other ion we're concerned about in electrophysiology, or the electrical activity of the nervous system, is sodium ions. And that distribution is the opposite of the potassium ion distribution. So sodium has a higher concentration outside the cell compared to inside the cell. So that's how I'm going to draw. Another thing we have to remember is the principle of diffusion. So we said that diffusion is any substance that wants to go from an area of high concentration to an area of low concentration. So if I were only looking at the potassium ion, there's the distribution of potassium. If I were to open potassium channels, which way would potassium want to move? Potassium wants to move out of the cell. Potassium wants to go from an area of high concentration to an area of low concentration. So that's the direction that potassium wants to move. It wants to leave the cell. On the flip side, if I were to only look at the concentration of the sodium ion, let's look here. Sodium, high on the outside, low on the inside. If I said that I open sodium channels, which way would sodium want to move? If I open sodium channels, because of the principle of diffusion, all substances want to move from an area of high concentration to low concentration. So if I open sodium channels, sodium would want to go into the cell, because any substance wants to go from an area of high concentration to low concentration. So remember that. Don't forget that. That was something that we learned a couple chapters ago. And I said, you're going to have to know this. This is why we're studying these ions and the chemistry of life. This is it. So you have to remember that principle. So make sure before we move on, you have this down pat. So you can pause the video and write this down. And as you're writing it down, make sure you're making yourself some notes. Like all substances move from an area of high concentration to low concentration. And when you're talking about ions and the directions that ions move, you have to talk about one ion at a time. So which way is potassium going to go versus which way is sodium going to go? Okay. So if I go back to the neuron, right? There is what we call when an excitable cell is at rest. That means it's just doing its normal job and nothing is bothering it, right? So for a neuron, we would say there's no stimulus, nothing causing change. So if we were to go in and measure the inside of this cell and see what its voltage is, the inside of a neuron at rest is at negative 70 millivolts. So this is the what we call the resting potential of a neuron. So you have to remember this value here, negative 70 millivolts. Don't forget the units, don't forget the negative sign. Okay? All cells remember, have a high concentration of potassium on the inside, high concentration of sodium on the outside. Ooh. Right? So just like I drew with this circle here, that's the case for this cell. So the inside of the neuron sits at negative 70 millivolts, negative 70, all down the axon. And the ion distribution is just like we drew here, except it's in this, funny shaped neuron. So let me clear this. So if we were to look at the inside of the cell, it has a lot of potassium, right? On the inside, and a ton of sodium on the outside. So this, nothing new. It's still the ion distribution. It doesn't matter that the shape is different of the neuron versus a cuboidal cell versus a circular cell. The ion distribution is the same. Now, when we start this electrical activity of the neuron, we always start it from rest. So do you remember what the resting potential is of a neuron? The resting potential of a neuron is negative 70 millivolts, right? Negative 70 millivolts. So I'm just going to draw this again. You're going to get so sick of this drawing. Okay, so it's sitting at negative 70 millivolts. That's at rest. Now I'm going to tell you that something is coming up and it is going to be a stimulus. And stimulus is anything that causes change. So if I were talking about the neurons in my eyes, the stimulus would be light. If I were talking about my sensory stimuli, my sensory receptors associated with my skin, the stimulus could be touch or pressure or pain or even temperature, right? So the stimulus is anything that causes change. We're just going to say stimulus for now, but I want you to wrap your head around what a stimulus is. Stimulus is anything that can cause change. So if we have a stimulus here, right? We apply a stimulus. Again, if this were a sensory neuron, maybe the stimulus would be actual physical touch, right? Touching the skin. And I'm telling you, the stimulus opens sodium channels, right? So now sodium channels, let's see if I can take this eraser. I didn't really, oh gosh, wait, hang on. So we're going to open sodium channels. So I'm going to make a little opening there. Now remember, the inside of the cell has a high concentration of potassium compared to the outside. Outside has high sodium compared to the inside. So if this stimulus opens sodium channels, which way is sodium going to move? All substances want to move from an area of high concentration to low concentration. So I'm telling you and showing you that sodium is going to move into this cell right here, right where the stimulus is. So if the stimulus is touch, I'm opening sodium channels, sodium rushes in. Again, why does sodium rush in? All substances move from an area of high concentration to low concentration. So if this region here, let's see if I can make it, let's make it blue. If this region here was originally negative 70 millivolts and some positive sodium entered, would it still be negative 70 millivolts? No, it wouldn't. And it goes stepwise more positive. So if a little bit of sodium comes in, remember sodium is a positive ion. So if a little bit of sodium comes in, maybe the inside right here goes from negative 70 millivolts to negative 69 millivolts. More sodium comes in, we go negative 69, negative 68, negative 67, negative 66, all the way up. You need the stimulus to keep the sodium channels open to have the sodium come in, okay? So right here is where the sodium is coming in. Over here, nothing's happening. So over here, what is the inside of the neuron reading? It's reading negative 70. I didn't draw any sodium here, so it's still negative 70. Over here, negative 70 millivolts, right? The only place where there's change occurring is where the stimulus is occurring, okay? And that right there is called a graded potential. A graded potential is called a localized potential, and that's just a potential difference in charge. So when we change the charge a little bit, it's happening very localized, right? So it's happening here. It's not happening along the entire cell. It's just happening at a very localized area until enough sodium enters to hit what we call threshold. And this is the next number that you must commit to memory. Threshold is negative 55 millivolts. Threshold. And we can think of threshold as the point of no return. And threshold is the beginning of action potential. So we talked about a graded potential. Now we're going to move into the action potential. So let's go from the drawing of the neuron to graphing this out. So I want everyone to draw this graph at home as I'm drawing it here. Whenever you have a graph, you label your y-axis and your x-axis. The y-axis is labeled in millivolts. We're going to label the x-axis as time in milliseconds. So this is happening really fast. It's a lot to learn, but it's happening in milliseconds. What we're graphing, so this is something I also want you to write down in your notebook. What we're graphing is what's happening inside a neuron during an action potential. So what's happening, we're graphing what's going on inside that neuron. First thing we're going to graph, first number we're going to put up on this graph is resting potential. So does everybody remember what resting potential is? Resting potential is negative 70 millivolts. I don't have to write millivolts here because I labeled my y-axis in millivolts. So resting potential just means that this neuron is sitting at negative 70 millivolts over a certain amount of time. Then we're going to apply a stimulus. I tell you what the stimulus does. The stimulus could do a bunch of different things. for this example and for this class, we're going to say that a stimulus opens sodium channels. You can always put in the corner of your paper to remember this ion distribution of all cells, including neurons. Okay? So if we say that the stimulus opens sodium channels, which direction does sodium want to move? Sodium wants to go from an area of high concentration to an area of low concentration. So we say that sodium enters the cell. Well, we're graphing the charge in the cell. So what's happening to the charge inside the cell? If sodium is a positive ion and more positive ions are coming inside the cell, then the charge inside the cell is increasing. It's going up. Why? Because sodium is entering the cell, and sodium is a positive charge, right? We say Na+. So if positive ions are entering, the inside of the cell is getting more positive, okay? This little curved line here is showing you the graded potential. That means it's very localized until we hit threshold. And threshold is the point of no return. So once we hit threshold, the action potential begins. So we would go from graded potential to action potential. Threshold is negative 55 millivolts. So at negative 55 millivolts, if enough sodium enters that neuron to reach negative 55 millivolts, we get, let's see here. I'm just going to erase this. Special, let's call this threshold, which is the beginning of your action potential. And then all of the sodium channels open. So instead of it just being here, it would happen all over. So all of the sodium channels open, and the inside of the cell goes from negative 55 to positive 30. Positive 30 is the last number that you have to remember. So positive 30 millivolts, negative 55 millivolts, and negative 70. At positive 30, two things happen. Sodium channels close, and potassium channels, open. Sodium channels close, potassium channels open. So when potassium channels open, which direction does potassium want to move? You look over here to look at your ion distribution. You see that there's more potassium inside compared to outside. So potassium wants to leave the cell. The charge of potassium is positive. So if potassium positive leaves the cell, the inside of the cell becomes more negative, right? If positive ions are leaving, the charge is going down. The charge goes down, it might go down a little bit more and goes back to rest. Let's review that one more time. And then the next time we meet, I will go over this with you one time all together in the classroom, and then I'll show you how it kind of works in the neuron and the shape of the neuron. This is happening at specific areas of the neuron, and it's happening over and over and over again. So it's not as easy as just a circular cell. Let's just review it one more time before we stop this video. First thing we do, we draw our graph. We draw our graph, we label our axes. Millivolts on the Y, time in milliseconds on the X. We start at rest. Remember, this graph is showing you the change in charge inside of a neuron. So we always start at rest. Resting potential is negative 70 millivolts. going, going, going. We have a stimulus. The stimulus causes sodium channels to open. Which way does sodium go? Sodium goes into the neuron. Sodium goes into the neuron. Sodium, which is positive, goes into the neuron. So the charge inside the neuron goes up. It goes up stepwise, stepwise, stepwise until we hit negative 55. Negative 55 is called threshold. So that's the point of no return. That's the beginning of action potential, right? Can't take it away. Once threshold is reached, that neuron's going to fire. So at threshold, voltage-gated sodium channels open, all of them open, sodium rushes in. If sodium rushes in, the inside of the neuron continues to go up until we hit positive 30. At positive 30, sodium channels close, potassium channels open. Which way does potassium go? Potassium wants to leave the neuron. Potassium is a positive charge. If positives are now leaving the neuron, the inside of the neuron is getting more negative. This is the graph of the action potential. One other thing that I want you to be able to label are the phases of the action potential, right? So the threshold right here is where we begin action potential. So this is where we begin. Then as the inside of the cell becomes more positive, this phase is called depolarization. As the inside of the cell returns to rest, that's called repolarization. RE for repolarization, RE for return, and RE for rest. So when it returns to rest, remember rest is negative 70. And then if too much potassium leaves and the inside dips below rest, where you see here, that phase is called hyperpolarization. Woo! It's called hyperpolarization. And you see that right here below rest, and then eventually the cell will go back to rest. It rebounds back to rest at negative 70. So again, this is what's happening inside the neuron during, first part is graded potential, second part is action potential. You will have to graph this for your exam. So please, please, please practice this. And then when we meet again and we go over chapter 11, we can continue this idea, but you will know sort of the ins and outs of action potential. And then I'll kind of try to put it into context with two neurons and how these electrical signals kind of communicate throughout the body. All right, thanks everybody.